Hello everyone, my name is Zach, and these words are scary. But they are important enough to confront head on, and understand exactly what they mean to yo-yo design, especially before I wheel out the second lesson in the series, which is going to wield these concepts heavily in order to explain design for performance. In Lesson 1, I put some fairly interesting graphs up near the end about how weight distribution and performance were related, mainly the relationship between rim weightedness and average angular velocity. I'm going to begin by explaining what that relationship is. Contrary to what you may have thought, energy is not conserved. Or rather, mechanical energy is not conserved. Or rather, mechanical energy is not conserved a lot of the time, but it can be conserved sometimes. Physics has a lot of asterisks, I know, but that's because it's a science that is simpler in terms of pictures and equations than the terrible communication methodology that is the English language. Pertaining to yo-yos, because, mostly, nothing is slipping and nothing is colliding, mechanical energy is fairly well conserved. That means that if you took a picture of a yo-yo right before you released it from your hand with a throw, and then took a picture of the yo-yo right after it hit the bottom of the string and started sleeping, you could look at the amount of energy before and after and say, yeah, okay, these amounts of energy are about the same as each other, or rather, that they are equal to each other. But not all forms of energy are equal. And there are a bunch of different forms of energy, but the ones we need to talk about here are linear kinetic, rotational kinetic, and gravitational potential. Linear kinetic is when an object with mass travels in a straight line at a specific speed, like a train carrying a massive pile of anvils. Rotational kinetic is when an object which is difficult to get spinning gets spinning at a certain angular velocity, like a tornado full of sledgehammers. And gravitational potential is where energy is added to a system when you move something against gravity, and energy is removed from the system when you move something with gravity. The first picture has a lot of linear kinetic energy and a little bit of gravitational potential energy, while the second has only rotational kinetic energy. It's algebra time. Linear kinetic energy is 1/2 mass times velocity squared, gravitational potential energy is mass times height times Earth's gravitational acceleration constant, and rotational kinetic energy is equal to 1/2 times angular velocity squared, which is how much rotation happens per unit of time, times a secret little letter that I will explain shortly. This one magical little equation contains nearly all of the information describing how a yo-yo performs. In fact, using this equation and changing our state frames a bit, putting the sleeping yo-yo in state 1 and the stationary yo-yo returned to your hand in state 2, you can actually calculate the minimum angular velocity at which the yo-yo could return to your hand on its own. Pretty cool, yeah? But enough bragging about how cool this equation is. It's time to talk about the elephant in the room. This is the letter I, and it is something called mass moment of inertia. Flashback time. In 1604, Galileo rolled a bunch of balls down an inclined plane while investigating what he would later call the law of falling bodies, which was the first ever experimental verification that the acceleration due to gravity occurs at a squared relationship with respect to time, but this is slightly irrelevant. This experiment also notably was one of the first well-documented cases of exploration into how intrinsic properties other than mass could impact how fast things rolled downhill without slipping. As I passively mentioned approximately 6 paragraphs ago, that not slipping part is very important, so keep that in mind, but stick with me here. What Galileo tangentially touched on is that somehow, although gravity was pulling on 2 different balls in the exact same way, and even though they weighed exactly the same as one another, one would get down the ramp faster than the other would. The punchline: different geometries resist rotation differently. And this letter I, the mass moment of inertia, is a number representing how difficult it is to change the rotation speed of this object. This means that if you rolled 2 different round bodies down a plane with no initial velocity and therefore no linear kinetic energy, that even after they've both traveled the same distance, meaning even after they've both absorbed the same amount of energy, the one with the higher mass moment of inertia resists rotation more and therefore absorbs more of that energy as rotational kinetic energy, despite the fact that it is spinning slower. And now all we have to do is pretend the plane is now vertical and turn the ramp into a string, and we've just teleported from 17th century Italy back to today's yo-yo conversation. We have now proven that yo-yos with higher moments of inertia spin slower and convert more energy from our throws into rotational kinetic energy. However, this is only the end of the beginning. Now, the real fun begins. Why would people want a yo-yo that has a higher or lower moment of inertia? Great question, and I won't go into too much detail now, but the essence of it is that yo-yos with lower moments of inertia make for better loopers and 4A yo-yos, whereas yo-yos with higher moments of inertia make for yo-yos with higher stability, like those used in 3A and 1A. They also boast longer sleep times because a lower angular velocity implies less friction. I'll talk about this more in later videos, I promise. But there's a key issue here that needs to be addressed. Moment of inertia is complicated. So complicated, in fact, that MIT professor of physics and famed educator Walter Lewin responded to a request for a simple explanation of it like this.
So is there a simple way of explaining why?
No, it's not simple.
No.
No, you need calculus even. No, it's not a simple way. No.
And he's right. Even if you just, say, wanted to determine the moment of inertia of a stick at an angle around an axis, you do indeed need a modest amount of integration coupled with some other elementary calculus. How can you know what your yo-yo's moment of inertia is easily, and once you have that number, so what? The normal way to determine the moment of inertia of something is to use a lot of really ugly calculus where you integrate over the domain of the radius, multiplying each time by the mass area of each infinitesimal section, and it gets pretty ugly trying to do this without actual numbers. However, there is a graphical way to do this problem. By drawing your yo-yo out to scale and approximating the amount of cross-sectional area your drawn profile occupies at each discrete layer, you can manually achieve an approximation for both the mass of the yo-yo as well as the moment of inertia of the yo-yo. However, once you have undergone this painstaking process and finally gotten a number out of it, you will have no idea what that number means. Is the number you have gotten for your moment of inertia an actually good moment of inertia? Is it too much or is it too little? You will have no reference point for what the appropriate moment of inertia is, and to make matters even worse, the entire scale of what a good moment of inertia happens to be will change as the total mass of the yo-yo changes. If you note the moment of inertia of a perfectly playable yo-yo at 62 grams and try to design a 70-gram yo-yo to have the same moment of inertia, the heavier yo-yo will rip off arms and embed itself in ceilings. Yo-yos at different weights tend to have different moments of inertia. This all gets maddening after a while, and this is usually where a hard split occurs between various yo-yo design philosophies. The mathematical planners see this split and just kludge their way through at whatever mass they end up at, despite the fact that tweaking a yo-yo's profile to increase the moment of inertia might very well change the mass, making the previous assessment you did completely invalid. And the more artistic yo-yo designers just seek to design yo-yos that they feel will perform well, and then finely tune their design sense after a significant amount of practice. However, there does exist an alternative design methodology to rectify this issue, and it is normalizing the center of area of the quarter section with respect to its maximum radius. Essentially, you take a drawing of the quarter section and you find its center of area, or where you would put your finger if you wanted to balance it. It's also called the centroid in some applications. Look it up if you have the time. So you take the distance that point is from the central axis, then divide that number by the radius of your yo-yo, and then multiply by 100 in order to turn it into a percent. Please note that I usually do this before I drill the hole for the axle, which, admittedly, does cause some issues for the accuracy of this mathematical model if your yo-yo ends up using a relatively long axle, but I'll talk about that in the next video. On average, these numbers range from about 50% to 65%. Where a yo-yo near 50% tends to regen well and may sometimes feel unstable in exchange for a pleasurable throwing experience, whereas a yo-yo near 65% will feel stable, if not almost too stable, and will sleep for a significantly longer time. There do exist yo-yos above and below this spectrum, but for aluminum yo-yos, typically 6061 aluminum yo-yos, with diameters between 50mm and 60mm, with widths between 39mm and 47mm, most yo-yos fall into this range. Lighter yo-yos tend to be in the higher end of this range, and heavier yo-yos tend to be in the lower end of this range, while keeping in mind that having a longer axle will end up pulling you down the chart. So, we've just done something pretty cool here. Using these last few minutes of the video, you can effectively run a sanity check on your design mid-process to see how normal your designs are, but there is one massive train of thought whose rails we've arrived at: when yo-yo designs become impossible in real life. And on that note, you're more than ready for Lesson 2 on Design for Performance. Thanks for watching.